So we're now entering a new unit where we're going to be talking about groundwater. And this unit's divided into 2 or 3 sections, the first of which is going to be somewhat review and more informational, which is this lecture, Properties of Aquifers. The next couple will be more engineering, more demonstrational with more equations and looking at flow to wells and just groundwater flow in general. But here we want to define a bunch of terms and just gain a basic understanding of what we're going to be talking about and what groundwater is like. You may have talked a little bit about some of this stuff in geotechnical engineering. You'll see some familiar concepts a little bit later on, but we kind of need a basic understanding of where we're headed before we go there. So when we use this term aquifer, we're talking about a geological unit which can store and supply significant quantities of water. And there's a couple of different kinds of aquifers. They're usually referred to as either consolidated, unconsolidated, or semi-consolidated. A consolidated aquifer is one that's essentially made out of rock, so sandstone or carbonate rocks, volcanic rocks that can hold water, versus unconsolidated or semi-consolidated aquifers, which are soil-based. There's a couple other things we need to define: confining layers or aquicludes, or impermeable layers, geological units with low hydraulic conductivity. So they restrict movement of groundwater either into or out of adjacent aquifers. And we'll look at a diagram on the next page that's going to show some of this stuff all together. Unconfined aquifers are ones that are closer to the surface. They have a water table. So they have their upper surface is free to rise and decline. So if I have fairly an aquifer that's close to the surface where recharged water from the surface is allowed to percolate down into that aquifer, it will have a water table. That water table is at 0 gauge pressure. It separates a saturated zone below it from a it's probably moist but unsaturated zone above it. And that water table can go up and down as storage in that water table aquifer goes up and down. Versus a confined aquifer where we have, it's an aquifer that's overlain by an impermeable unit like an aquiclude, and that aquifer is under pressure and the water level can rise above the confined unit in a well. We'll look at that again in a second. And in this case, in the confined aquifer case, we have something called a potentiometric surface, where with a water table aquifer, with an unconfined aquifer, we can say, if we want to say what's the head in that, the head is the water surface elevation, right? Just like we're in a tank. Whereas in a confined aquifer, we want to say what's the head in there. The head is actually above the top level because it's under pressure. And so the head is the potentiometric surface. So let's look at that diagram here. Here's an example layered aquifer system where we have impermeable strata is this hatched area. We have a confined aquifer, which is this bottom one. So recharge areas where it may rain up here, or there may be a pond or river or something recharging this area that's permeable. That permeable area is between these two impermeable layers. And for that confined aquifer, there's this piezometric or potentiometric surface at the top that represents the head in here, right? It's sort of like an energy grade line that's coming down here. So when I puncture a well down here into this confined aquifer, water, because the potentiometric surface is up here, water will flow in and out through the well. And this is called an artesian aquifer, an artesian well, that I could just poke in the ground. I could drill down and it will just start flowing. And that's because the recharge area is higher elevation than where the well was drilled. Versus I could drill a well over here into that confined aquifer Here the piezometric surface is just below here, so it's not going to flow at the surface, but the water level is going to be right where that hatched line is. And then here's a well that goes down into this unconfined aquifer that's over top of this confining layer. So the water percolates down and hits the confining layer and starts filling up. So here's the water table. I puncture the well down into there, and the water level is going to rise to the water table level in that well. This concept of recharge, here's a little diagram. Recharge is where is the water in the aquifer coming from? I might be pumping some out, but how is it being replaced? So there's natural forms of recharge in the form of precipitation, melting snow, or lakes or streams that can be infiltrating all the time. Or artificial recharge, like the opposite of a well where I have a pump that I'm pumping water out of the aquifer, I could actually be pumping water into the aquifer to artificially recharge it. And that can be like treated wastewater, for example, is a place where this might happen. There's places where we want to try to resist saltwater intrusion, and so sometimes we pump fresh water in near the ocean to keep saltwater from infiltrating down and into our aquifer. And so there can be artificial recharge wells there too. Reservoirs, so if I build a dam and a reservoir fills up behind it, that's artificial recharge where maybe before the stream that was going through would only have a limited recharge. Now I have a reservoir there year round that's probably infiltrating some amount of water into the aquifer all the time. Okay, so a couple other terms. Porosity, you should have learned about in geotechnical engineering. This is the percentage of rock or soil that's void of material, so it could be air, filled with air, or water. And it's the maximum amount of water that soil or rock can contain when it's saturated. It's expressed as a ratio of the volume of the voids to the total volume, so it's this little n, V sub V over V. Here's a little table where it shows different kinds of materials and the porosity. Keep in mind that the same type, the same texture of soil could have different porosities depending on whether it's well graded or poorly graded. So this is a well graded soil where everything is the same particle size and there's a lot of porosity, versus a poorly graded soil where you have a lot of different particle sizes, so these little guys can fill the voids and your porosity goes way down. So this is an important concept just to understand how much water could unconsolidated aquifer hold based on its porosity. Particle size distribution, you've also probably learned about this with sands, silts, and clays. You may have seen this triangle, percent sand, percent clay, and percent silt. You can get your percentages of those three types located on this triangle and figure out what kind of soil you're dealing with. So if you have a lot of silt, you're over here in silt. A lot of sand, you're over here in sand. A lot of clay, you're up here in clay. And then everywhere in between with these like sandy clay loams or loams, that sort of thing. And again, here's the particle size classifications, basically for these things. And there's different metrics or different tables and sources you can go that define it differently, but that's the basics. So I go through this and the porosity that are review for you because you'll see them pop up in other tables. For example, when we're talking about specific yield down here, there's a table here that says for different types of soils, what are porosities and specific yields and so forth. Okay, so what is specific yield? Specific yield is what portion of the groundwater from an aquifer drains under the influence of gravity. So we have an aquifer and water's infiltrating through it. Some will continue to infiltrate and just move through, but some of that water gets left behind because the type of soil or rock that it's moving through has some amount of surface tension or ability to restrict the water flow and actually retain some amount. So the specific yield is the volume that would drain under gravity over the total volume. So if you look at this table over here and you look at the specific yield for different types, clays do not want to give up water. They will retain that water for a long time very tightly, and that just has to do with the actual structure, molecular structure of the clay layers. So clay has a specific yield of 2, or 0.2. This is values in percent by volume, 0.02 or 2%. So very low specific yield versus sands and soils that will yield a lot of their water just via gravity. Hydraulic conductivity, K, you've talked about that in geotech, also called permeability. It's an indication of an aquifer's ability to transmit water. How easily does it flow through the aquifer? So the more gravelly and sandy you are, the faster or the easier it is to transmit water. And the values here are in our velocity values. We'll talk in the next lecture about a little bit more about what that means, since it's not really a direct velocity like particle velocity like we're used to, but it's in this distance per time units. So 0.1 to 1 centimeters per second for gravels, and then it goes down as you go towards clays, which do not want to transmit water very easily. So we'll use this a lot, but we'll also use this other term, transmissivity. Transmissivity is the product of K, the hydraulic conductivity, and whatever the saturated thickness of the aquifer is, B. So this little b is the thickness of the aquifer. If we go back up to this diagram, B for this unconfined aquifer, the thickness would just be the height from down here to up here. And for the confined aquifer would be, again, the height from here to here. So it's how thick is the aquifer, multiply that by K, and you get this transmissivity, which is capital T. And this is one of the major parameters of concern in groundwater calculations and analysis. You can measure it through a number of tests, which I'll talk about in a later lecture. Pump tests, slug tests, tracer tests. You can also just get it by taking soil samples and measuring the hydraulic conductivity in a permeameter, and then use well logs or drilling logs to figure out what the thickness of the aquifer is, and calculate it that way. So you'll see T show up in the equations we'll talk about in the next lecture on flow of water to wells. And then these last two are essentially use the same equation. So there's the storage coefficient or storativity. Sometimes it's called one, sometimes it's called the other. This relates to the water yielding capacity of an aquifer. And it's defined as the volume of water that the aquifer releases from or can put into storage per unit surface area per unit change in piezometric head. In other words, S equals the volume of water divided by the surface area divided by the change in the head. Okay. It's easier to understand what this means in terms of the aquifer yield, which is the same equation just rearranged. The volume of water drained from an aquifer as the head is lowered. It's the same equation for storativity. So how much water comes out? If I have an unconfined aquifer and I lower it by 1 foot, how much water comes out? Well, that's the storativity times what my surface area is, times that 1 foot that I lowered it. So that storativity value, there's different ones for different kinds of aquifers. And again, the storativity relates to both the specific yield and the specific retention. There's actually an equation for the storativity that's based on the specific yield and specific retention values that I'm not presenting in class, because typically we will, as an engineer, we'll look up a value of S for different soil types, or we'll have a geologist report to us what the storativity is. And so again, like, this lecture gets into kind of this gray area between engineering and geology. There's hydrogeologists, which typically come from a geological background, And then there's civil engineers, which, they work together a lot, but there's a sort of a dividing line between when you get into the really nitty-gritty of the stuff that's going on in the groundwater. That's more of a geologist's ballpark, versus civil engineers, which are dealing mostly more with wells, and in some cases it might be like contaminated subsurface water where we're trying to treat it, or it could just be drilling wells and then extracting it for water supply purposes or something like that. So when we get into the actual parameters that have to do with the aquifer itself, again, that's mostly more of a geologist's realm. And so this is just a very quick, broad overview of some of these terms that we're going to see come up again and again as we look at the equations for flow to wells that we'll start in on the next lecture. Okay, and that is all.